Hello, this is Ms. DB, and in this lesson we're going to continue with Chapter 12, Section 1 on Introduction to Sequences, and we're going to focus on writing rules for sequences. So in some sequences, we can find the value of a term when we don't know its preceding term. If we know the preceding term, we can just use a recursive formula, and we can just keep adding the same thing to the previous term, or sometimes multiplying or squaring or whatever. But an explicit formula is when you define the nth term of a sequence as a function of n. So it works for any value of that specific sequence. Now, we can't do it for every sequence. Sometimes it's too complicated to find them. But the ones that we're going to look at is when we have a linear pattern, or if we have an exponential pattern. Now, quadratic patterns, we've looked at those before. They have constant second differences, but they don't match with an arithmetic or a geometric sequence that we know a nice explicit formula for. You can use your reasoning skills and figure out a formula that will work for them, or you can run a quadratic regression with those values at Desmos or on a graphing calculator. But quadratic ones are, interestingly enough, quite difficult to set an explicit formula for. So we're going to focus mostly on the arithmetic, which will be the linear pattern, and the exponential, which are the geometric. All right, so let's look at this right here. The first thing that we have to do is figure out, is it linear pattern? Is it a quadratic pattern? Is it an exponential pattern? So we do that by looking at the differences, the first differences, the second differences, and if neither of those are the same, then we look at the ratios. So here we have our terms listed, and we subtracted 4 minus 1.5 is 2.5. 6.5 minus 4 is 2.5. 9 minus 6.5 is 2.5. All of our first differences are the same. That tells us that this is a linear pattern. And if it is a linear sequence, a linear pattern, then we can use the explicit formula for an arithmetic sequence with a common difference. And the common difference is going to be the same as the first differences. And we use the pattern a sub n equals a sub 1, which is the first term, plus n minus 1. We'll leave the n will stay in your formula, minus 1 times d. So we'll replace the a sub 1 and we'll replace the d. The n will stay and we'll leave the a sub n at the front. Okay, so the first term, that's our a sub 1. Each term is 2.5 more than the previous. That's our d. So we plug those into the formula, and we get that. Did they write that in a nice? Yeah, here's our nice rule. A sub n equals 2.5. That's our, they flip-flop this around a little bit. Actually, theirs looks a little different than ours, doesn't it? Here's if we use this formula, I forgot to plug it in first. So then we'd have 1.5 is our a sub 1, that's our first term, plus 2.5, that's our common difference. It's just written at the front instead of the back, like in this example, times n minus 1. And then we just simplify that by using the distributive property and adding like terms. So we'd have 2.5n minus 2.5. So let's write what we'd have. We'd have 1.5 plus 2.5n minus 2.5, and then we combine our like terms, which is 1.5 minus 2.5, and we get minus 1. So this form is just simplified of the explicit formula, finding the nth term of an arithmetic sequence. So simplify if you can. All right, let's look at another one. 7, 5, 3, 1, negative 1. Look first for the first differences. If the first differences are constant, then we have a linear pattern. So if we subtract 5 minus 7 is negative 2. 3 minus 5 is negative 2. 1 minus 3, they're all negative 2. That's a constant first difference. Therefore, this is a linear pattern, so we can use the arithmetic explicit formula for arithmetic sequence. This common difference, or this first difference that is a constant, is also equal to our d. And our first term right here is 7, a sub 1. So we can plug those in. Let me plug those in before we see what they rate. So I'd have a sub n, you'll keep that, that's like your y equals, and then we put a sub 1 is 7, plus parentheses n, we leave our n there, minus 1, times d is negative 2. Now I'm going to simplify this because it's pretty messy. So a sub n is equal to 7, and now I do the distributive property. I take negative 2 times both of these parts. Negative 2n, negative 2 times negative 1 is plus 2. And now I combine my like terms, which are 7 and 2. And I'm going to put the negative 2n in the front here. Plus 9. Or you could write it as 9 minus 2n. Either one would be correct. So that is, and then we can check that by plugging in, let's say this is ACE 1, 2, 3. This is our fourth term. If I put 4 in here, do I get 1? If n is equal to 4, I should get 1 back. So I would do 9 minus 2 times 4. 9 minus 8 is 1, so this works. So it works for that one, and it would probably work for the rest as well then. And that's just them doing the same. Here's some problems from your worksheet that are very similar to this. So the first few on your worksheet, 1 through 4, are all going to be linear arithmetic, just like we just did. So the first thing we do is we write the first differences, and we do that to verify that this is linear. If it's not linear, you can't use this explicit formula for arithmetic sequences. So we find our first differences. So we take 1 minus 3, that's negative 2. Negative 1 minus 1, that's also negative 2. Negative 3 minus a negative 1, negative 3 minus negative 1, that's the same as negative 3 plus 1, so that's also negative 2. And negative 5 minus a negative 3 is the same as negative 5 plus 3, so that's also negative 2. So we do have common or constant first differences. If these are the same, then this is also the common difference, d. So d is equal to negative 2. The first term is just you pick the first term that's listed, and that is 3. So now we use this to write our equation, but we're going to have to simplify it. So a sub n is equal to a sub 1, which is 3, plus n minus 1, leave the n, times d is negative 2. Whoops. Now we simplify this because this is not written very neatly yet. So I'd have a sub n equals 3 plus, now do the distributive property. I'd have negative 2n plus 2. And then you combine your like terms, and I would get 5. And I can either write minus 2n, or I could write this as negative 2n plus 5. And then you check by plugging in some values. This is, let's say, this is term 3 right here. If I use 3 for n, do I get negative 1 as my answer? So negative 2 times 3 is negative 6, plus 5 is negative 1, so it worked for that one that I tried. So I'm going to go with that as my answer. So that's how you'll do the ones that you first figure out if they're linear, or verify if they're linear, and then if they are, that's your common difference, the constant difference, and then you use this format and just simplify it a little bit. So you might find it a little bit easier to use a slightly modified form of this where the d is written first and then the n minus 1. That might make it a little bit easier to do your distributive property. All right, let's look at this one. This one is not linear. 5, 10, 20, 40, 80. If we look at our, boy, they did that quick. If we look at our first differences, we would have 10 minus 5 is 5, 20 minus 10 is 10, 40 minus 20 is 20. The first differences are definitely not constant. So now we'll look at our second differences. So 10 minus 5 is 5, 20 minus 10 is 10, 40 minus 20 is 20. Those are also not constant. If neither the first differences or the second differences are constant, then we want to look at the ratio. For the ratio, you can look for two things. It works either way. You can either look at the ratio of the second differences. That's what we did in chapter 9. So we would say 10 divided by 5 is 2. 20 divided by 10 is 2. The problem with using the ratios of the second differences is we don't have very many. You can also look at the ratio of your original values, your original sequence. So I'd go 10 divided by 5 is equal to 2. 20 divided by 10, I'm just taking these terms here, is equal to 2. 40 divided by 20 is equal to 2. And 80 divided by 40 is equal to 2. So we get a few more values there. And we do find that the ratio is constant, and it's 2. That tells us that this is an exponential model. Exponential. And it so happens that the exponential model is going to fit the geometric sequence formula. So we can use the a sub n equals a to the 1, the first term, a sub 1, times r, the common ratio, the same ratio as what we found when we did our ratio on the previous page, to the n minus 1. Now the n will stay in the formula. So what we would do for this one is we would write a sub n equals, now we change our a sub 1, we replace that with our first term of 5. We replace r, I'm going to put it in parentheses with 2 because that was our common ratio, and we leave the n minus 1. Now they're doing it a little bit differently. They're trying some different things and seeing if they can figure out the pattern. But it just so happens that the pattern is going to match the geometric sequence explicit formula. So we might as well, if it's exponential pattern, then use the geometric sequence explicit formula. So here's an example from your worksheet. Let's check and see if it's either linear or exponential. We don't really have a good one to use for quadratic. And if it's either of those two, then we can use one of these formulas that's written at the bottom of the page in order to write the explicit formula. If it's quadratic, we have to run regression or just figure it out. All right, so our first difference is we take 3/4 minus 3/2. Now, you might think that this is fractions and that this is nasty and awful, but it's really, if you have a fraction calculator, or if you want to change them to decimals, or you can just practice with your common denominators. So I'm going to just do common denominators. I'm going to change the second fraction to fourths, and I would get negative 3/4. So that's my first difference. Then I'm going to take 3/8 minus 3/4, and I need to change 3/4 into eighths, so that's 6/8, and that is negative 3/8. So I already can tell that my first differences are not constant. So I'm going to, well, I'll do one more. 3/16 minus 3/8. So I'll change my second fraction to 16ths, and I get negative 3/16. Definitely a pattern here, but they're not constant. Now I'll check the second differences. Let me change my pen here. I'll take negative 3/8 minus a negative 3/4, so that's the same as plus. So I'd have negative 3/8, change this to eighths, and I'd have 6/8. So that's 3/8. And then I'll take negative 3/16 minus a negative 3/8 would be a plus, and get a common denominator of 16ths. So that would be 3/16. So these are, the second differences are not constant either. So let's look for the ratios then. I'm going to do the ratio of the original values because I only have 2 to check. I didn't go very far with my differences. So I'm going to take 3/4 over 3/2. Now, in order to simplify this, I'm just going to multiply top and bottom by their common denominator of 4. And these cancel, and I'd have 3 for the numerator. And this would be, goes in there 2 times 3 is 6, so I get 1/2. That's my first ratio, is 1/2. Okay, for my second ratio, I'm going to take 3/8 over 3/4. And then I'm going to get a different color here. I'm going to multiply top and bottom by the common denominator of 8 this time. And I'll get 3 over, this goes 2 times 6, which is also 1/2. So it's looking like the ratios of the terms are going to be constant. Let's do one more. 3/16 over 3/8. Multiply top and bottom by the common denominator of 16. And I get 3 over 6 again, which is also 1/2. So I have a common ratio, which means that this is an exponential sequence, which means that I can use the geometric explicit formula right here. My first term is 3/2. R is equal to this here, 1/2. And I can just plug those in. So I'm out of room down there, so I'm going to write it up here. A sub n is equal to a sub 1, 3/2, times r, which is 1/2, to the n minus 1. And we don't really simplify the geometric ones at all. We just leave it like this. This would be our answer for number 6. This is just an example that is neither, the first differences are not constant. We'd have 1/2, and then I don't even know what they are. The second differences are not constants. The ratios are not constant. But this one just has a very simple pattern. We could even write this as 1 over 1. Our first term number is 1. Our second term number is 1 over 2. Our third is 1 over 3. Our fourth is 1 over 4. So sometimes our sequences are just, you just look at them to figure out what they are, like this example. So our rule for this would just be 1 over n. So if you're looking for the 100th term, it'd just be 1 over 100. So every once in a while, you'll see one like that. Here's some application problems. A ball is dropped and bounces to a height of 4 feet. That's our first term. The ball rebounds to 70% of its previous height. 70% of 4 feet would be 2.8 feet. Graph the sequence and describe its pattern. How high does the ball bounce on its 10th bounce? So here it is graphed. We start at 4 feet. And then I take 70% of 4 and I get 2.8. And then I take 70% of that and I get 2.8 times 0.4 is 1.12, and so on. And then we have to figure out if this is, let's make a little table here. So our first one was 4, and then we had 2.8. So I have to take 2.8 times 70%. Oh, sorry, it's 1.96. I think I said something else before. So it's almost 2. And then I take 1.96 times 0.7, and I get 1.372. I'll go one more. And then I take that times 0.7, and I get 0.96. So you can look at the graph and see that this is not linear. So we don't really need the first differences. You can probably also look at the graph and see that it's not quadratic, because a quadratic will go down and then come back up. However, it does look exponential. It looks like exponential decay, like it's decreasing and then kind of leveling off and going to kind of follow along there. So let's look at the ratios. Let's take 2.8 over 4, and then take 1.96 over 2.8, and 1.372 over 1.96. Let's see if this is exponential, because if it's exponential, we'll find the common ratio, and then we can use this as our geometric explicit formula. So it's 0.7, interesting. Maybe we should have realized that. 1.96 divided by 2.8 is also 0.7, because each time we multiplied by 2.7 or by 0.7 to get to the next one. So our common ratio is 0.7, which is the 70%. So R is equal to 0.7. Our first term is the 4. So we're just going to write this as a sub n is equal to 4 times 0.7 to the n minus 1. And then, was there another part we were supposed to do? Here's our, I think we were supposed to answer after 10 bounces. So to find out where it'd be after 10 bounces, you take your formula, your explicit rule, and you replace n with 10. So now it's 9. So then you would take 0.7 to the 9th power. So 4 times 0.7 to the 9th power. Do the 0.7 to the 9th first. So we'd have 4 times, here's what I got on my calculator, 0.040353607. I'm not going to actually write that down on paper. I'm just going to leave it on my calculator and now multiply that by 4 to get 0.1614144. So that's approximately 0.161 foot, or they change it to inches. In order to change this to inches, you can multiply this by 12, because there's 12 inches in a foot, which gives you about 1.937 inches. They said about 2 inches. So that's how they did, we do that application problem. Okay, this is optional. So if you've had enough, you can go do your worksheet. If you want to learn about how to do the quadratic sequences, when there's a quadratic pattern, you can continue listening to this video. So in this example, we do our first differences, and we get 6 minus 3 is 3, 11 minus 6 is 5, 18 minus 11 is 7, 27 minus 18 is 9. Our second difference is 5 minus 3 is 2, 2, and 2. Our second differences are constant. So this is quadratic method, or quadratic model. So in order to find the rule for this, you can sit here and kind of figure out what I could do. I could take n and maybe I can multiply it by 2, or maybe I have to square it and then I'll add something. You can work through it. And there's videos on how to do this, and there's some real complex explicit formulas. But another way that we can do this is we can use Desmos. So I'm just going to quick sketch down we have 3, 6, 11, 18, and 27 as our values in our sequence. And if we go to Desmos.com and use that regression feature that we've used quite a bit this year, I'm going to first put a table in. And my x values are just the term numbers. So I have 5 terms, 3, 4, 5. And then the y values are those parts of the sequence. We had a sequence was 3, 6, 11, 18, and 27. Now we're going to run a quadratic regression on this. So y1 is approximately equal to a times x1 squared plus bx1 plus c. And you can see that the points were graphed up here. Let me move it down just a little bit. There's our points. And that this r squared value is exactly 1, so it's fitting it perfectly. And they give us values for a, b, and c to use as your equation. So the equation for this would be, I'm going to use y right now, and then I'll go back to the worksheet. Plus, oh, I forgot to put that a would be 1. B is 0, so we don't even need that. Plus C is 2. And it fits that exactly. That is the equation that fits our sequence. So if we put this back into the sequence notation with, a sub n and a sub 1 and such, let's go back here to our, we would have so it was like this. It was y equals 1x squared plus 0x plus 2. But we're going to change this to 1n squared plus, we don't need 0n plus 2. So let's check this. Does a sub n equals n squared plus 2 work? So at our first term, n equals 1, we would have 1 squared plus 2. That's 1 plus 2 is 3, and that is what we got for our first term. At n equals 2, our second term, we would take 2 squared plus 2, and that's 4 plus 2 is 6. And that is what we have for our second term. And we'll do one more, n equals 3, we would have 3 squared plus 2, that's 9 plus 2 is 11. Now, you could probably figure this out just trying some different things and looking for patterns. Or you could use the Desmos to help you find, a pattern. All right, well, thank you very much. Have a wonderful day, and let me know if you have any